for Unit 4 fields. I think last class, Miss Linda took you guys through a free body diagram experiment. Um, so today it's just going to be pretty straightforward. We're going to basically understand what a field is and how they relate to like particles, and those particles are either charged or not charged. You're going to be able to create a free body diagram related to fields, and then just a simple calculation on electric fields with the Earth's surface. At the end or around like 2 o'clock, what you guys will have to do is do a quiz on quizzes. I think it's a website you're kind of all familiar with right now. Um, but I think the key thing for this one is probably you guys will need to submit it by the end of class. You're more than welcome to ask me any questions during class about the quiz. I'm here to help you guys and make sure you guys get a pretty good grade. Okay, so let's get started. So yeah, you guys should be able to, I guess, just follow along on the whiteboard. I'm going to be writing some notes, and if you guys want to copy it down and have it in your notebook, that'd be great. But yeah, so okay, so let's start by definition. So let's define what it means to talk about a field. Okay. So in this case, what we want to know is basically there's three key parts. So you want to know that it's going to have some form of a charged particle. It's going to be either positive or negative. The second part, it's going to be there's going to be basically an electric a gravitational or electric field around these charged particles. So there's going to be a field, and we'll only cover two fields, basically gravitational and magnetic. So you don't have to worry about. There's like many other fields when it comes to like maybe like higher level physics, but this one it's just gravitational and magnetic. Um, and then the last part is that the electric field space, I guess, or both field space basically exert an electric force that we're gonna need to calculate. So this part is gonna need to be calculated. Okay. So yeah. So let's see this. I think this diagram does the pretty well. Oh. Oh, one second. Okay, well, I'll just draw it on here. So, okay, so let's just say we have a charged particle right here, and it's going to be positive, okay? So what you basically are going to see maybe on a test or an assignment is these lines protruding from this charged particle. And the lines aren't most important, it's mainly the arrows on these lines. So in case of a positive charged particle, the electric field lines are just going to be pointing outwards, like basically away from the particle here. Okay. And that's for a positive charged particle. Then for a negative charged particle, I'm sure we can all know what's gonna be the field lines are gonna be pointing towards the particle. So I guess this kind of explains a lot why a battery has a positive and negative end of a terminal, because basically when you have like the negative charged particles always like to like consume, and positive particles always like to exert. So there's always going to be that like base that creates like this, I guess you can say, well, energy being created between the positively charged particles and negatively charged particles. So here, okay. Right, and one more thing, if you see for notation wise, it's going to be Q. So you're going to have plus Q, which means it's a positively charged particle, and a negative Q for a negatively charged particle. Now, what you'll see is there'll be coefficients out in front of these variables. So sometimes you'll have 2Q, you can have like basically like 3Q, um, up to like all the way up to like NQ, and NQ just represents like any of the natural numbers, so it can range from like negative infinity all the way to positive infinity, and that's all the values. So we know that any particle, charged or not, is going to have some coefficient, some aka some value out in front. So in this case, if there's a particle that you see maybe in a question or an assignment or whatever, that it says like 2Q plus, so that free body diagram is just all it's going to really require you to do is just draw double the lines of what the original Q. So let's just say this Q only had 5 directional lines pointing away from the particle. 2Q would have like 10, and then 3Q would have 15, and so on and so forth. So I guess I'll just, for demonstration, I'll just draw it in. Okay, and then the same, I think we can agree it's going to be the same, just the directional lines will be pointing towards the particle for negative 2Q. So negative 2Q. Okay, but I won't draw it because okay. So all right, so that's basically charged basically what happens when you have two particles. So now that what we're going to cover next is basically like what happens to these interactions between the charged particles. So basically applications. So and don't worry if you're not. I'll post these notes after on Google Classroom so you guys can have it along with like the document. Okay, so let's just see some applications with this. So I'm gonna see if there's a form share or no no screenshot. Okay. So actually, hold on, I think this was the diagram I was trying to show you guys. Okay, and I'm gonna ask a question in the chat. Okay. Okay. So can everyone see in the chat that screenshot I just took? Just put a thumbs up, yes or no, or okay, great. So what I want you guys to see, and I guess I'll just ask this question in the chat and you guys can respond. So out of A, B, okay, so A, B, and C, which, okay, so let me just post, one second, I'm just writing out the question in the chat. Okay, so let me just describe what's happening here. So you'll see like in image A, you'll have a positive electron, and then like we discussed, their electric field lines are always being exerted out, and it's going to be attracted to the negatively charged particle over there. So so that's that flow of electricity right there. What's like basically what I'm trying to ask is, can you describe what's happening in part B the same way? Like, okay, so we have basically two positively charged particles. is that gonna are they attracted or repelled in part B? So let me just post that, and then you guys can just post it in the chat if you agree or not. So in diagram B, are the particles attracted or repelled? Like, are they being attracted or repelled? And I'll give you guys like about like 2-3 minutes to answer this question. So there's no rush, and then I'll post another question for part C. But in diagram A, we can all agree that the particles are being attracted to each other. Okay, yeah, that's good. Yeah, okay. Okay, great. And I think Lorena and Yasser, they answered me in the private chat, which is perfectly fine. That's okay. So yeah, the charges should be repelled, which is good. In diagram C, basically what you're seeing here is essentially like it's still the positive and negative being attracted, but there's this weird thing happening with that negatively charged particle. And when you see something like this, all that's happening is basically there's a stronger charge. So that positively charged particle is not on the same magnitude as the negatively charged particles. So you can see that there's a lot of field lines, like a lot. Like I think there's like twice or three times more field lines from the positive to the negative. And that just means that the magnitude in the positive particle is higher than the magnitude in the negative. So I'll just write that up. Okay, great. Okay. Okay, so that was the diagram. Now, okay, so now we're just going to switch back to the applications, and then I think we'll do a practice problem, which I'll let you guys work on for about like 5 minutes, I think is fair enough. But let's get these applications done. So basically, um, what we want to talk basically, okay, application. So um, when there's a charge, a bunch, well, a lot of charged particles, the it's called a phenomenon because I mean it's at the end of the day it's just static, but it's kind of cool because like yeah, if you think about like how static is like you don't see it, right? Well, we do feel it, and I guess you can say you can see it, but originally, like you can't go to your cabinet and like or your pantry and be like, oh, I want to pick out static or whatever. Like it's not something, it's not a physical object. So when we say it's a phenomenon, it's like it's kind of like something that naturally happens. So I guess I won't put that in, but when there's a lot of charged particles in a contained area. The result is static. Okay. And so this obviously, the application of static is not, basically what happens when you have static is, for example, it's very dangerous on an airplane. So I guess I'll, here, uh, static electricity on an aircraft can be extremely dangerous. And so basically what you'll see is here, I guess I'll actually, yeah. Uh, So this would be like a typical, I guess, a short answer question on your test. So I just asked for like, give me an example of when static could be potentially dangerous in a real world example. And in this case, it would be you just give the example that it's on an aircraft. Um, I guess the diagram here, I'll post it in the chat so you guys can see it as well. Um, if you guys ever flown on a plane or basically have sat in the a window seat, you'll see like on the wing of a plane, there's these like basically rods, and you would I would also assume you would see these I guess these little like stuff dragging around the back of a car during the summertime, especially during summertime, because like the surface of your car gets like very hot, and when you're driving it's like there's very dry air, so there's a level of friction between the air and the surface of your car, and basically that friction is what charges these particles up. So when you go and like touch the surface of your car, like the human body is also like a conductor of electricity, so the current technically doesn't pass all the way through you, but it's just like it just that's the result of like the static is that like that minor discharge between like anything that like touches the surface of it. So these rods on the end of the plane basically capture all of that static. So if you can imagine like on that surface of the plane, it's basically like here, I'll draw it on the whiteboard. So let's just say for simplicity's sake, like this is the wing of a plane. Okay, let's just say like it's a straight box, for example. Okay, it essentially is. It's just a sheet of metal, right? And as it's like, as the plane is going through the air, it's going to encounter a bunch of like wind current. So it's like the wind's blasting this sheet of metal, right? And then over time, what you'll have is all these charged particles, which is like represented by these small little dots. Like, and it's covered. Actually, wait one sec. Let's do this better. Hold on. Okay, fine. I'll just draw a bunch of dots as much as I can on here. Okay, so all of these like charged particles are going to be like basically rubbing around each other. Like they're going to be moving around a lot. And so with these rods is that they're basically going to get filtered out, if that makes sense. Like, so essentially, if you can imagine all of these charged particles moving around, and then all of a sudden they have like um almost see these rods as a discharge connection. So the moment a charged particle goes on one of these rods, it's just going to like stay on these rods. It's not going to travel back onto the surface of the plane. But now the accuracy on how much these rods actually capture is not known. But what we do know is that it reduces the level of sorry, it reduces the level of static friction significantly. So I think that would be like a solid yeah. So just if you can explain that, then I think you'll be good for a short answer question on the test or whatever. Um, Another application I guess you guys would see is like lightning rods on condominiums and stuff like that. So here again, I guess like even if you just say like a lightning rod, that I think that's fair enough too, because as long as you have an external point away from the structure of the building where like the charged particles can just go and hang out for a little bit, if you can think of it like that, then that's basically any preventing static from being around your building. So now with this ground wire over here, or sorry, with the lightning rod over there, it is attached to a ground wire. So um yeah, I'll just show you guys. I think diagrams are really useful too. So okay. So question in the chat that I'm gonna post to see if you guys are getting where I'm going. Um, true or false? It'll just be a true. Just tell me if it's true or false. So true or false?
Um, True. Okay, so does having a having a lightning rod a building create for need to have a ground wire? Okay, so the question in the chat is, and you guys just can tell me true or false. Does a lightning rod have to have a ground wire? And so I think okay, key true. Okay, perfect. Yeah. So okay, Yasser, Lorene just she messaged Lorene did say her answer before she left, so it's okay. Yasser also told me it's good. Okay, good, great. You guys all said true, which is the answer. Yeah, so essentially like the reason why we need a ground wire is because like to transfer the flow of electrons. So the answer is true. Okay, great. All right. Okay, so let's do a practice problem now. So we get the understanding of what's happening here through some math. Um, hmm. Okay, right. Okay, calculate the magnitude and direction of the electric field 30 centimeters to the right of a point charge Q microcoulomb. Okay, okay, great. So here's the question. Let me just write it out. So practice question number 1. So we say calculate the magnitude and direction of the electric field that is 30 centimeters to the right of a point that is charged with minus 3.0 microcoulombs. Okay, so for notation wise, I just put U, but it's supposed to be like um, I guess I'll write it out here. 1 sec. So I'll get you guys started on this question. So basically, remember what we talked about. There's going to be you're going to use the grasp method. So GRASP. So you want to start with what you're getting. We do an analysis stage where basically you write out the formula that you're going to use, and then you write your solution, and then you just paraphrase basically your findings. So you say like in this case they asked for the magnitude and direction, so you just paraphrase by saying the magnitude and direction of the electric field um, would be blank and blank. Okay. So that's okay, so that's that part. The solution part, you guys are going to work through it. I'll give you the analysis. So basically the formula that you guys are going to be required to use. So remember we covered the formula E is equal to KQ over R squared. So K, and then the constant, I will provide that as well. KQ squared, or sorry, KQ over R squared. Okay. That's your formula that you're going to be using. The required section. Basically, what are we looking for? So we are looking for E, the value of E. Given, we're going to be given our K value, our constant K, which is 9.0 times 10 to the 9 newtons meters cubed sorry, Newton's meter squared over Coulomb squared. Okay. What else are we given? Let's I think let's read the question again. Let's see. Okay, so we're given this value of okay, so we know okay, let's back it up for a second. Let's just understand what the question's asking us for. Um so we have basically these two there's basically two charged particles, right? And because the magnitude and direction of the electric field, remember, an electric field can only be um created between two charged particles. And if that charged particle is going to be a positive and a negative, then one of them is going to definitely have a greater level of charge. In this case, we know it's the negative value. So this guy is going to have more. Um, so his electric field lines are definitely going to be more towards here. Okay. But you don't need to draw the diagram. I'm just trying to illustrate what's happening visually. Okay. And then obviously, like the diagram I posted in the chat, there's going to be some like weird kind of like all these lines around it um, going towards the negatively charged particle. But and it's like it's kind of weird because it's like these like the lines exerting from the positively charged particle don't actually go straight to the negative charged particle. Like it does that weird like all these weird lines and stuff. But I don't I don't know. So it's never just like straight, like, okay, you have a two particles lines are going straight. No, it's like it's very scattered. And I think that's where the energy gets like lost. Like so but anyways, so okay, so we know K, we know our value of C too. It's gonna be microcoulombs, which you got to be careful because microcoulombs are a lot smaller than normal coulombs. So you have to basically convert it. So -3 microcoulombs is actually 3 times 10 to the, wait, 3, sorry, 3.0 times 10 to the -6 coulombs. And then we're given that basically they're both separated by a distance of 30 centimeters, or remember, we always convert to standard units in physics, so it's meters. So 30 gets divided by 100, which is just 0.3 meters. And yeah, so that's, yeah, okay, so great. Yeah, and I think that's all we need to really solve this question. So yeah, so I'll give you guys about, what is it, 136 right now. I'll give you guys till 140 to complete to post a solution. Just in the chat, send me a message, and then we'll take up the actual solution. So we'll reconvene at 140.
Okay, so I think I just will give you guys about 2 more minutes. You guys are just need some extra time, so can reconvene at like 1:42. So some students are asking me to for some extra time, so I'll just give you guys some extra time. Okay, I think I think I got all the answers from Hala, and yeah, I got both answers. I'm sharing my screen because I'm using an online tool called Desmos. Great, it's honestly amazing. I really like it because you can even graph different stuff. But we'll get into the graphing part later. So let's just compute it. So we have 9.0 times 10. 1 second. 0 times 10 to the 9, and that represents your value of k, and then you're going to multiply it by 3.0 times 10 to the oh, oh, this one. Hold on. Sorry, 1 sec. My calculator is a little bit lagging. Okay, there you go. Sorry. There. Okay, 9.0 times 10 to the 9 is our value of k. And then that's going to be multiplied by 3.0 times 10 to the negative 6. Okay. Okay. And then all you got to do is just highlight it all to divide it. And then we go 0.3, which is our radius, squared. Okay. So your final answer should be 300,000 newtons coulomb, or in scientific notation, it will be, or I'll just switch back to the whiteboard 1 second. Here. Okay, so what I basically wrote in the on the calculator was E. Oh, the analysis part will be E is equal to K K times Q all over R squared. And then this is equal to basically 9.0 times 10 to the 9
I won't include the units because it just gets like very messy, especially on the whiteboard because I'm using the tool, but it's through my mouse, like through the I guess the trackpad, so it's kind of like it's kind of difficult for me just to write out the units because it's very small. So 9 point, so I'll just write out the values. So 9.0 times 10 to the 9 is what we have for K. Q, remember, is our value of the charged particle, but we converted the microcoulombs to coulombs. So negative 3.0 microcoulombs is actually 3.0 times 10 to the negative 6. 0 times 10 to the negative 6. And what you guys will notice is that um the direction. So I guess you can say, because you can ask like what happened to the negative out here, and that's a valid answer because if you go back to the Desmos calculator and you basically try and 1 second, let me pull that up. Okay, so you put in negative for that value, and you are going to get a negative value, or you can just say that it's pointing towards the negative electron. So I guess you can include it because I did forget about it in the here, I'll just take another screenshot. You guys have it. Um, okay. Oh, um, okay, great. Oh, oh, I can't do that. Okay, never mind. Okay, just always remember, yeah, just put in the negative value because it will change it won't change the value of the answer, but it will change the perspective of the answer. So it's still going to be 300,000, either way if you include positive or negative, but the perspective on the answer will change. Which is meaning that you're in your paraphrase, you would say um the direction as well. So yeah, let me just finish this question. And then divided by basically 0.3 squared or 30 0.30 squared. Okay. Okay, great. So that's gonna get you a value of minus 300,000 or um or minus 3 times 10 to the negative 5. Okay. So okay, great. So that's your answer. And then let me just finish up. Oh, paraphrase, right? So, okay, so we'll scroll down here. Okay, so now we can complete it saying that um, the magnitude and direction of the electric field would be minus 300,000 and to the and pointed toward the negative electron. Okay, great. Okay, so um, okay, thanks. Did you guys have any questions for me about that question or anything else we covered so far? Okay, no, okay, so no one got a question. Great. Okay, so I guess for the rest of the class, I think the quiz is posted, and I don't want you guys to rush through the quiz because it is a form of evaluation that we do take a look at. So it's not something you should rush through it too. It's something you should actually understand and take your time through it. So I think I'm giving you guys a fair amount of time. Like there's 1 more hour left in the class, and I think there's plenty of time to complete it before that, which is what we're trying to do is basically see if you guys can do some in-class work and then submit it at the end of class. I think that's pretty fair. And then at the end of the day, you guys can really ask yourself, you did complete the quiz, and do you have a chance to get 100% really? Because I can, be assistance and help you guys with any questions you need. So let's let's switch over to there. So let me um let me just stop sharing my screen for a second. Okay, so the quiz is, let me see if it's on Google Classroom. You guys just give me a thumbs up in the chat if you guys do see a quiz posted. I think it there is. It's called Electric Fields. But I'll send the link in the chat so you guys can just click on it and get right to it. Um, I'm just gonna share my screen in 1 second so I can show you guys the quiz and have it opened on my screen as well. So okay, right. Okay, so great. Yeah, 22 questions. Honestly, if you guys like think of it like this, take 2 minutes per question and like really understand that. Like read it for 1 minute and then practice it, and then practice it for another minute, right? So um yeah, so here I'll share my screen. I think I see it now. Um okay, great. Yeah. Okay, so I'll just share my screen. And we can go through the first question together because I think it's pretty straightforward. Okay. Can everyone see my screen? Just give me a thumbs up in the chat or say yes. Okay, great. Okay, great. Um, okay, so let's see the first question here. So, it asks us which of the following statements is false about electric fields. Okay, electric fields lines are always straight lines. Electric field lines point away from positive charge. Electric field lines cannot cross. And D, electric field lines show how a proton would move in an electric field. Okay, so question says which of these are false. So, oh shit, sorry. My screen just, uh, oh, so you guys can't see my screen. Sorry. Yeah. Okay, sorry. Okay, sorry. So this says which is the false. So what did we cover today? So um we basically we know electric field lines can cross, so that's true. Um, electric field lines show a proton would move in an electric field. We know this is true as well because the key word in this question is electric field, and we know that to have an electric field, there needs to be two charged particles. It could be a proton and proton, a proton electron, or in the other cases, which is we're not going to cover in this course, it could be like quadruple protons and like two electrons. Like it could multiply in different variations, but aside from that, you need two charged particles for an electric field. So that's true. Um, Question A: electric field lines are always straight lines. I think I briefly hinted on this, and so the answer is this one. This is false. Electric field lines are always straight. This is false. Because we know electric field lines point away from positive. That's easy. This is false. So, and essentially what that means is that it's never a straight line
to each other, and that's basically like I guess how like energy is really lost is when the lines are because the lines represent the flow of energy. So if you're we know in physics like the path to the most efficient path in direction is always a straight line, and the efficiency is also related to it's strongly related to um basically like how much energy something saves. So efficiency and energy are correlated. Um, but in this case, the energy lines are not straight. So that's false. Okay. Great. So yeah, that didn't take too long. I think like 2 minutes a question should be good. But okay, I'm gonna let you guys do so for question one, it's the answer is A, and then you guys are good to proceed to the next questions. And if you have any questions, just again, open the chat and let me know. And also, you guys can talk amongst each other too if you guys only to understand like within reason. I think collaboration is important, but you guys can discuss if you want. But turn on your mics and then you guys can talk about it. Okay, I'll let you guys work. And if you need any help, I'm in the chat and you just need to send me a message.